Up until this point in your calculus career, the main object of interest has been functions, specifically smooth functions of one variable. Using calculus, we can figure out critical points, where the function is increasing or decreasing, areas under the graph of the function, and so on. But a more basic property of a function that we've studied is just its limiting behavior. In other words, if I have a function that's defined for all x off to infinity, as I send x to infinity, does that function approach something? This is the question that we want to focus on now. But rather than study the growth of functions, I want to consider a discrete version of a function. This is what a sequence is. On my picture, a sequence is just going to look like a bunch of dots. I'll define this more precisely in a second, but it corresponds to a list of numbers, and I call that list of numbers a(n), where a1 is the first number, a2 is the second number, a3 is the third number, etc. On my picture, a1, this number would be the height of the function at this dot. a2 would be the corresponding height for the second dot, and so on. Given a bunch of dots like this, I can ask the same question that I did about a function. What is its limiting behavior? As I send n to infinity, do the dots approach anything? So more precisely, a sequence, which I'll write a sub n, or sometimes with brackets. This is just a list of numbers, a1, a2, a3, a4, a5, and so on. Just to see some quick examples before we do some more intensive examples in a second, the most classic sequence ever is probably 1 over n. What this means is that this is the list of numbers 1 over 1, which is 1, 1 over 2, 1 over 3, 1 over 4, and so on. Another example would be the sequence bn equals 3. This is a really boring sequence where every number in the list is 3. It's the constant sequence, just like the constant function 3. This next definition will be imprecise, because making it precise requires some math that we don't really want to talk about right now, but I think you'll know what I mean. So given a sequence, we will say that it converges to a number L if the values of the sequence get closer and closer to L as n goes to infinity. In other words, take the usual notion of the limit of a function as x goes to infinity and apply that to our sequence scenario. As n gets bigger and bigger and bigger, if your list of numbers approaches some number, L, we say that the sequence converges to L. So let's revisit our quick examples from a second ago, the first of which was the sequence 1 over n. This list of numbers was 1, 1/2, 1/3, and so on. And if I drew those on a picture, they would look sort of like this. Now, if you look at the list, each number is smaller than the number before it, and if the denominator is just going to keep getting bigger and bigger and bigger and bigger, we'll have 1 over huge numbers. Those are very close to 0. And it seems like as n gets bigger and bigger and bigger, this list of numbers is approaching 0. Nothing groundbreaking, but this is our first example of a sequence which converges. The limit of this sequence is 0. As a quick remark, the sequence 1 over n corresponds to the function 1 over x. So what we just did is the same thing as asking, what's the limit of the function 1 over x as x goes to infinity? Similarly, if we consider that other sequence, 3, as n gets really big, all the numbers are still 3. So, in particular, this sequence converges, and it converges to 3. The limit of 3 is 3. Pretty mind-blowing stuff. Like I said, we'll see some more interesting examples in a second, but before we do that, I just want to introduce the rest of the language that we'll use, which is that if a sequence doesn't converge to a finite number, or if the limit doesn't exist at all, we say it diverges. So the possibly new language here is that a sequence converges if the limit exists, and if it doesn't, if the limit doesn't exist, or if you go off to infinity or something, we say that it diverges. Okay, some quick examples of diverging sequences. What if we looked at the limit of n? Well, the sequence n is the list of numbers 1, 2, 3, 4, etc. And as n gets bigger and bigger and bigger, well, those numbers get bigger and bigger and bigger, and they go to infinity. So we could write that the limit of n as n goes to infinity is infinity, which is to say that the sequence n diverges. Some people will use language like diverges to infinity or something more specific, but I'm not too concerned about that right now. Either of these statements are fine in my book. Now that's kind of a boring one, so more interestingly, here's another sequence. -1 to the n. If I were to write this out as a list, what would we get? Well, when n is 1, -1 to the 1 is -1. When n is 2, -1 squared is 1. And then for every odd number n, we'll get -1, and for every even number, we'll get +1. So this sequence alternates between -1 and 1 forever and ever and ever. If I drew that in a picture, it would look something like this. And the question is, do these dots get closer and closer and closer to some number as we go off to infinity? The answer is no. They just bounce back and forth between -1 and 1 forever. They never settle down towards a certain height. So in this case, we just say that the limit of the sequence -1 to the n does not exist. It's not infinity, it's not 0, it's not 1, it's not -1, it just doesn't exist. In other words, it diverges. I have two main examples I want to consider to demonstrate some more sophisticated techniques in figuring out limits of sequences. The first of these examples is to evaluate the limit of natural log of n plus 1 over n squared. Now, just like with functions, given a limit, the first thing we should do is just try to evaluate it directly. In other words, just take the limit of each piece and see if that gives us the answer. So I'll just do this part in my head, but if I look at the numerator and the denominator separately, the numerator is natural log of n plus 1. We know that the behavior of natural log, as the input gets bigger and bigger and bigger, the output gets bigger and bigger and bigger as well. This happens slowly, but natural log does grow to infinity. So this tells me as I send n to infinity, the numerator is going to infinity. Here it's helpful to think about the graph of something like log of x. The denominator is the same scenario. N squared is going to go to infinity as n goes to infinity. Those numbers get bigger and bigger and bigger. So if we were to try to evaluate this directly, well, it wouldn't work because we would get infinity over infinity, and we know that this is an indeterminate form. Something like infinity over infinity, we cannot determine the value without doing more work. It could be infinity, it could be 0, it could be 7, we have no clue. Now you might be tempted to say, oh, I could use L'Hopital's rule. It's infinity over infinity, that's indeterminate, take derivatives and go from there. This will effectively be our solution, but I want to be a little careful here. This is going to be a little picky, but it's the kind of thing that I want to think about carefully. L'Hopital's rule is about limits of functions. In particular, it involves taking derivatives. What we're dealing with is a sequence. The sequences in the numerator and the denominator are not smooth functions. They're just dots. Can you take the derivative of a dot? No, you can't. Now you should object and say, well, Joe, you've been drawing smooth functions between the dots, and you've been talking about how they're basically the same. So can't I just pretend that these sequences are smooth functions so that I can take derivatives? And in this case, the answer is yes, you can. So there's nothing fishy that happens here. But, as we'll see in our next example, this is not always the case. So this is why I want to talk about this. It may seem like doing sequential limits is always the same as just doing the limit of a function, but this isn't true. A lot of times, like this example, it is, but not in general. Anyway, so rant over, what do? I do want to use L'Hopital's rule. This seems like a situation where I could apply it, and the first thing I'll do is I'll switch to a function of x so that I know I can take derivatives. So this first step might seem a little silly, but I'll start out by saying the limit as n goes to infinity of log of n plus 1 over n squared, the thing I actually care about, a sequential limit. This is actually the same as the limit as x goes to infinity of log of x plus 1 over x squared. Again, it seems like I probably didn't do anything. I just changed the letter that I'm using as my variable, but to me there's an implicit underlying meaning saying I can extend my sequence to a smooth function to take derivatives and use L'Hopital's rule. Now from here on out, there's nothing new. This is just the limit of a function. The top goes to infinity, the bottom goes to infinity. So L'Hopital's rule applies because this is an indeterminate form of infinity over infinity type. So by L'Hopital's rule, I can individually take the derivative of the numerator. This would give me 1 over x plus 1. Divided by the derivative of the denominator, this would be 2x. And we can evaluate this limit instead. After some simplification, we get 1 over 2x times x plus 1. And this one's easy. As x goes to infinity, the top is constant, the bottom gets really, really big, and we get 0. And we're done. The limit of this sequence is 0. Now, just as a quick remark, roughly this is showing us that powers of n grow more quickly than logarithms. Our sequence is a ratio of a log on top and a power of n on the bottom. Because this fraction went to 0, this is telling us that the bottom got bigger much faster than the numerator. This is an important general kind of thought process to have in a calculus course like this. It'll come up a lot. Okay, I've got one more main example to look at. This will be to evaluate the limit of the sequence quantity n minus 1 squared over something called n factorial. In case you haven't seen factorials before, let me just tell you really quickly what this means. So the exclamation mark reads as factorial. So n exclamation mark, out loud, this is n factorial. And the value of this expression is the product of all numbers up to and including n. So abstractly, n factorial is 1 times 2 times 3 times 4, all the way up to n. For some specific examples, 3 factorial would be 3 times 2 times 1, which is 6. 4 factorial would be 4 times 3 times 2 times 1, which I think is 24. Then this one's going to be hard for me. 5 factorial is, well, 5 times 4 times 3 times 2 times 1, which is 5 times 24, which is 120. Now this is an important thing to observe. Notice how I did this last computation. 5 factorial is 5 times 4 factorial. In general, n factorial is n times n factorial. This kind of computational trick will come up a lot in this course as well. Okay, so now that we know what factorials are, let's do the same kind of thing we did in the previous example. Before doing any fancy techniques, I just want to see if I can evaluate this directly. In other words, evaluate each piece by itself. Well, in the numerator we have n minus 1 quantity squared. As n goes to infinity, these numbers are going to get really, really big. It's a positive power of n, so the numerator goes to infinity. The denominator is n factorial. And based on the examples in the top right corner that we talked about, it shouldn't be surprising that as n gets bigger, n factorial gets bigger and also goes to infinity. This should make sense. If you just keep multiplying by more numbers, they're just going to get bigger and bigger and bigger. So just like in the previous example, when we try to evaluate this directly, we get an indeterminate form of type infinity over infinity. It may be tempting to say, okay, well, I'm just going to do the same thing and use L'Hopital's rule. In this situation, this does not work. It doesn't work for a couple reasons, but the first of which, based on what I talked about in the previous example, L'Hopital's rule involves taking derivatives of smooth functions. But n factorial, at least as how I've described it, this expression only makes sense for whole numbers. Like 3 factorial or 4 factorial makes sense, but what is 3.5 factorial? What would pi factorial be? I don't know. So at least for our purposes, n factorial is only defined for whole numbers, so I cannot connect the dots here to come up with the smooth expression that I understand. In other words, x factorial doesn't really mean anything to us right now. We cannot turn this into a function, and therefore we can't take the derivative of this. That means that L'Hopital's rule is off the board. And just to think about this a little more, even if we could, like even if x factorial did make sense, what would its derivative be? I have no clue. So anyway, the point is, something like a factorial is very specific to a sequence. It's an expression that does not arise when you're dealing with limits of functions. We've actually already seen another example of this. Earlier I talked about the sequence -1 to the n. This is another expression that only makes sense for whole numbers. -1 squared is fine, -1 to the 4,000, that's fine. But what would -1 to the 1/2 mean? What about -1 to the pi? These don't make sense. In other words, -1 to the x is nonsense. So the quick takeaway before we actually do the problem is that when you're dealing with sequences, if you ever see something like n factorial or -1 to the n, the techniques like L'Hopital's rule don't work. So you have to do something else. And generally the game plan here is to use what we could call the Squeeze Theorem. I don't really like calling it that. To me, it's just using common sense with inequalities. But a Squeeze Theorem inequality type argument is usually the best thing to do with sequences like this. So we'll see what I mean here. So this type of argument might be a little weird if you've never done something like this before, and it takes some practice, especially with factorials, to get used to this. But let me show you how I would do this. Also, I will say that there are probably a lot of different arguments you could make. This is just the first thing that I thought of, but I encourage you to try to come up with different kinds of arguments to get the answer. Now, usually since factorials are so weird, when I have a sequence, I'll start out by just expanding out the meaning of the factorial. Algebraically, you can't really manipulate the expression n factorial without thinking about its true meaning. So the first thing I'll do here is I'll just say, okay, well, the thing that we care about is n-1 squared over n factorial. What does this mean? This is just n-1 squared all over n times n-1 times n-2, all the way down to 3 times 2 times 1. So I just wrote out the definition of n factorial in a particularly helpful way. Having done this, one immediate thing we could do is we could say, well, there's a common factor of n-1 on top and bottom. Simplification is almost never a bad thing, so we could just cross one of those factors out. That'll leave us with a simpler expression. I have n-1 over n times n-2, all the way down to 3 times 2 times 1. I just deleted that n-1 factor from the denominator. The next step is where things get a little tricky. Here's where you have to be a little creative. I'm basically just going to split this expression up into two different pieces that I understand better. My motivation here is if I look at the expression that I'm dealing with, on the top I have n-1. So roughly this thing is growing like n. On the bottom I have a whole bunch of stuff. I have n-2, all the way down to 3 times 2 times 1. So it feels like there's more orders of growth on the bottom than there is on the top. So I'm kind of thinking maybe I can absorb the growth on top with one of the things from the bottom, and then there will be extra stuff on the bottom to make the denominator big and bring the whole fraction down to 0. That sounded a little crazy, so here's what I'm going to do formally. I'm just going to rewrite this fraction as follows. I'm going to group the n minus 1 on top of the n in the denominator, and then I'll just multiply by everything that I have left. So the rest of the stuff would be 1 over n minus 2, n minus 3, all the way down to 3 times 2 times 1. Now the first thing to notice is that on the right side in the denominator, this expression is n minus 2 factorial, right? It's the product of all of the numbers up to and including n minus 2. The next observation is that the term in the parentheses n minus 1 over n, this is always less than 1. It's a smaller number over a bigger number, so it's less than 1. So here's what I'm going to conclude. This fraction that I care about, the one that I started with, by these observations, it's going to be smaller than 1 times 1 over n minus 2 factorial. Really, all I'm using is the fact that n minus 1 over n is smaller than 1. And this is true for all values of n. Okay, so let me recap what we've shown. We've shown that the thing we care about is smaller than 1 over n minus 2 factorial. The other observation is that this is always positive. It's a non-negative number. This is important, even though it seems silly. So I have an inequality like this. This is a setup for the squeeze theorem. The point here is that the thing on the right is much simpler than the thing we actually care about, and in particular, we already know that the thing on the right goes to 0. The top is constant, n minus 2 factorial is going to get really big, so this goes to 0. So I have something in the middle. On the left, I have 0, and on the right, the bigger thing is going to 0. This squishes the middle thing between zeros, and by the squeeze theorem, the limit we care about has to be 0.